I would like to say a few words to introduce Kristina, Schinegger and Stefan Rutzinger from Soma. I met them actually a long time ago when they were students here at the Bartlett. But I have to say, I was sitting in one of their juries at the time, and I think I was in your jury, but I completely forgot. Until more recently, I was part of this jury in Taiwan for the Taiwan Tower, and there was this absolutely fabulous, beautiful scheme which was constantly voted by all the members of the jury, up until there was a 6-hour-long debate about the first and second prize, and we couldn't make up our minds who was going to win this competition. And this was the scheme done by Soma and the scheme by Su Fujimoto. And it went on for 6 hours without us making any compromises for both sides. There were two groups, and we couldn't decide. And what happened in a way was that the competition had different phases, and one of the issues was that they went there to present the work. And each team had to write with their engineers, with the whole team, to introduce the scheme. And there was no doubt that this was the best presentation. Also, they had the best engineer involved, was Klaus Bollinger, who Peter Cook, a colleague from here, used for the Kusshaus graphs. And I remember we were all sitting there in this room, in this dark room, and there was the Austrian entourage there arriving and presenting their stuff. And there is Klaus Bollinger stepping forward and introduces the engineering. And he sort of points out a metal tube which was standing in the corner somewhere. And we all looked aside and said, well, that's the sort of most banal, standardized steel tube that you can get in Taiwan, the cheapest also. And that's the basic component for our tower. And then he started showing what it was about. And everybody was thinking, this is a great solution of engineering. This is a beautiful architecture scheme. But it's amazingly clever as well. And in fact, they unfortunately became second. But clearly, their work was 5 times less expensive, 5 times less, or had 5 times less use of material than the first scheme. And when we finished the competition discussions, we all knew the first prize was never going to build it because it was so enormous. I'm not going to get into the details of the thing. The point is, it was a great scheme, and at the end, when all those who were there to receive the awards, and they were there as well, we all then met at the end, and we said hello, and Stefan was saying, well, you sat in my crit, and I said, this is incredible. I sort of started remembering it finally, and then I was in touch with Marian, who was in touch with them. And he said, of course, you remember them, they were at Bartlett before. Now, without wanting to extend too much, which was interesting, or is interesting in their case, is that they studied at the School of Applied Arts in Vienna, in the Wolf Briggs studio, which is a very known and established school in its own right, and in a school of thought. And then they came to the Bartlett, and then they went to LA with a scholarship. And in fact, they crossed sort of across this triangle of London, Vienna, and LA in a very particular period. And I think these things are sort of not a coincidence. It's not a coincidence that a few years later you have the same team of people doing competitions and winning them, or getting a second prize and being almost up there. Because in fact they had been in touch with sort of the key players and the key issues that were going on. And they were just telling me that when they went to LA, they were quite fortunate to be in the Schindler house and have a lot of time free. What they did was to catch up with their computational skills. And in fact to get a lot of know-how, which became really important for what they're doing now. And thank God we had that time, because we probably won't have that time again. I mean, since then they built a fabulous piece of architecture, which is this theme building for the Expo in Korea and South Korea. There are 4 members that created Soma. Two of them are sitting in Salzburg, the other two, Kristina and Stefan, are sitting in Vienna. And there is also this beautiful building for the Building Academy in Salzburg. And when, during the last summer, we were in discussions with them to teach at the Bartlett, I remember your ear and Jonathan and others looking at these projects and saying, gosh, this stuff is really, really amazing. It's beautiful build, it's very complex, and they're very young teams, this is amazing. And when you have sort of members of staff being jealous of the other ones, of how good it is what they're doing, you realize there must be something really good about it. And then, much more recently, I was invited to go on a jury to the School of Fine Arts where Stefan was teaching. And the work was beautiful. Some of the students were doing superb stuff. And you sort of put all the puzzle together and think, they are a great team, they're very good architects, they came from great schools, they did strategically the right things in the right moment, and they obviously are very good teachers as well. And they should be part of our lectures and show the work to us. What I think is also important for all of us is that they are young. And that means that there's a sort of sense of immediacy of coming out of academia, keeping yourself sort of alive, teaching, doing all sorts of things, winning awards, but in fact starting to build. One of the issues that comes clearly from the Studio Prix group is that it has generated an enormous amount of real architects who build, who really, really are eager to build. And I remember to be part of a panel which went to evaluate the schools of Vienna, and we went to the Studio Prix class, and there was this room full of models of buildings, which were amazing. I mean, the tectonics were mind-blowing. And they came from this environment, so no doubt that these things are no coincidences, that it all matches up. So, look, I'm delighted that you're both here, that you're teaching here. Stefan Ritter, sitting just behind, has also joined the unit in teaching. And I pass my word to you. Thanks for giving us the talk. And it's going to be great stuff, I guess.
So thank you for the kind introduction. Oh, this is nasty, okay. Matt will be Matt. Okay, so, yeah, Markus has introduced SOMA already, so we are 4 partners, Stefan, Martin Oberascher, Günther Weber, and myself. We all met at the university and then spent some couple of years in offices working on other projects. But besides that, we were always doing competitions and projects on our couch in the living room. And finally, in 2007, then we started doing our own projects, and we decided to form our own office. So currently, we're having 2 offices in Vienna and Salzburg, and we have a core of constant employees. But then also we have a very vibrant group of students and interns who come in and out, and we really enjoy the exchange with the universities where we teach and academia, and I think that really nourishes our work. We named ourselves SOMA out of a double reason, so to say. In Greek language, SOMA means body, and in philosophy, in Soma aesthetics, Soma is the sentient, the living body. So, of course, we all perceive architecture with our body, not only through visual inputs, but also through proprioception and kinesthesia. But we are also interested in architecture itself as a mutant and constantly transforming body. So this bodily and atmospheric interaction between the two is at the core of our interests. Another reoccurring theme in our studio, these are now really very old projects, the projects we started our studio with, But a recurring theme is movement. So we're really interested in how perception and kinematics are intertwined. And this is a very early competition scheme for the new opera in Berlin, where we were trying to combine acoustic and visual triggers and create a music pavilion that we called synesthetic filter. And by the simple movement and rotation of these reflectors, it would combine visual and acoustic qualities of the space and create these instruments composers and musicians could play with. Another theme that we share, another interest, is our fascination for masses and volumes. So we're really interested in very simple elements that build up complexity, and doing this by rules you can manipulate. And we call these vague formations not only because the boundaries tend to be undefined, or they can grow or extend, but also because they have a certain potential to be expressive and evocative, and to be read and interpreted in many different individual ways by users. So they also have this kind of openness. In this case, this was what we did at the Schindler House. We were studying growth patterns of corals, and the base element is an octahedron that can change its state of phase from solid to sparse. And then we built it at the Schindler House as an installation that was actually breathing. So we had a latex skin and vacuum. And the breathing cycle was quite slowly. It took like 15 minutes. So it was really at the border of noticeability. And we really like this notion of a living organism. Another topic I will explain probably or come to later in the project is performance. So this is another installation we did this time in the Museum for Applied Arts in Vienna for the Lomographic Society, where they do these amazing colorful picture walls, collective picture walls. And we took the weak photo paper and bended it and created this three-dimensional interpretation of these walls. And by bending, the paper becomes stiff and actually has a material performance. And this is also something we're really interested in. We really convinced that if you do experimental architecture and you're very speculative and explorative, you need to prove that these things also behave in a novel and inventive way. So we really understand design as an ongoing process that has to be explorative, and our projects are rather outcomes of this process. So we're always happy if we find a brief or a competition where we can test something that we have developed. And this was this lucky case in the when we did the mobile art pavilion for the Salzburg Biennale. So this is the pavilion already there in Salzburg. As everybody knows, Salzburg is a very protected historic city center. Culturally, it really predominantly refers to its past and to Mozart, and you see Mr. Mozart standing in the right-hand side of the picture on a pedestal looking down at our pavilion. And you're really not allowed to do anything new in Salzburg. Even signs of big firms and brands have to be done as if they were old. So this was really something very unique to happen to bring a piece of architecture, of contemporary architecture, to the city. So what we decided was, since the pavilion was also traveling, that we would not embed it into any context, but rather create a very strong and distinct presence on its own. So something that would probably be as alien and look as strange as the sounds it would be emitting. It was, as I mentioned before, a pavilion for the Salzburg Biennale. That's a contemporary music festival. And what we took as a starting point for our proposal was the idea that rule and variation is inherent in architecture as well as in music. So contemporary music might sound really strange to our ears, but as soon as we start to engage with it and start to read its structures, we can really explore the very defined and controlled rules. So again, the rule is rather simple. layers of sticks in opposing directions that in principle create rather weak structure, and then by changing the angle they become performative, and they create a stiffness that's really very amazing. So we wrote this random script and just played with it, trying to find out how many sticks do we need to create this mass-like appearance, and testing and doing loads of variations with these linear elements. Oops. So the idea was really to create this flickering mass we would put there on the Mozartplatz, and we were also testing it in physical models, so that's really how we work. We do not believe in hand drawings anymore. We do hand drawings if we need to communicate very quickly in the office, but we rather like to do these three-dimensional diagrams and then really test the architectural effects spatially. What we were lacking, or what these outputs of this script did not have, was a structural evaluation. So we teamed up, as mentioned before, with these amazing engineers, Bollinger, Grohmann, Schneider, in Vienna. We are really happy since Klaus Bollinger was also our professor at the University of Applied Arts in Vienna. So this is really also something that helped us a lot doing this project. And they are doing a research at the University of Applied Arts with irregular structures, and they're also developing a tool called Caramba, which is a plugin for Grasshopper. So together with them, we built up a parametric model where we could control and evaluate the structure. And the great thing is that you now have a shared platform. So the engineer and the architect both manipulate the structure in one program. So it's not a before and after, but it's really a simultaneous process. So here you see how the evaluation takes place. So the sticks start to move slightly and search for improved position, so to say. So they try to reduce the joints and the distance between the joints, since joints means money. And by doing that, they also enhance the structural performance or decrease deflection or deformation. So in yellow, you see the deformation that would take place and how it gets better and better, and how in the end the white and the yellow overlay. So then you have a so-called optimized structure, of course, within the architectural intentions. So all the 1,500 aluminium sticks are the same, but they all have different joints, so it's actually a huge puzzle. So logistics becomes a crucial topic. You need to really name everything. So the model rules everything. The digital model is really what you are working on. You do not draw any more plans, since this would not have any sense. The only plans we were drawing was to get the ones we needed to get the building permission. And everything goes directly from the model to the CNC machines. And here you see also the picture. This is not on the left-hand lower side. This is not a joke. If you build with aluminium, you really have this precision within millimeters. And then you see how it's built together. It's actually a huge, huge puzzle. And this is the mock-up. We had to test if the deformation was really not taking place at all, because all the parts had to fit together. And we were also testing how these parts could be handled, so they could be transported to the different locations of assembly. Also, the interior is very modular, so you could react on the various events they would like to have in the pavilion. After it was used for the Salzburg Biennale, they also rented it out to other festivals. There were art exhibitions, design exhibitions, lectures, all kinds of events taking place in there. And we also had an interior membrane, since we also needed to protect it from rain, but you could also assemble it without the membrane. Yeah, this was the first assembly spot in Salzburg. It really had it got lots of very positive response from the audience as well as from the public, and it really was that strange appearance we were hoping to get. And when it was emitting these amazing sounds, it really was a perfect match for the music we found. And then it traveled to the rural valley of Krakautal in Austria, and it was really interesting how the change of the context not only changed the reading of the structure itself, but also changed the reading of the context. And it got even more weird when the artists took over with their strange ceremonies and performances. And after that, it traveled to Maribor, and in the next 10 years, it will be used, hopefully, throughout Europe. And also, it was nominated this year, among many projects, of course, for the Mies van der Rohe Award. So we were also very happy and delighted about that. The next project is the project that helped us to get the job at the Bartlett, as you all know now. So this is the competition for the Taiwan Tower. Actually, it follows quite the same idea as the Salzburg Pavilion, only in a much larger scale. But behind this design lies also this strategy of bottom-up, of building complexity out of very simple basic elements. Only that this time the tower is 330 meters high. So this is the site. It's a former military airport in Taichung, Taiwan. On the right-hand side, we see the master plan of the park, Stan Elm, a huge development. So it's a whole new city. And here is the site of the Taiwan Tower. And the Taiwan Tower should become the main landmark of this enormous park. The whole city development is planned to be zero carbon. So we were also looking at certain principles in nature, not only to get inspired and to get a geometry out of that, but also we were looking for certain principles we could embed. The other idea, I think this is now we can't really see that so well, but the other idea is to invent a new tower typology. Usually these observation towers have these cores. You enter, and then by magic you reappear 300 meters high up in the air, and you have this gap of experience. While we proposed an open tower typology where you could experience all the areas of the tower, you could have this open and free zone and walk underneath the tower, and you could also travel up between and along these open legs. So the tower creates an open field that is then filled up by the museum, and the park flows freely beneath the tower legs. And here you see the ensemble of museum and tower and all the platforms, the intermediate platform in the middle of the tower and also the head. And you're moving in transparent capsules along these legs, and it really becomes a spatial, three-dimensional experience where you also have a changing panorama of the city and the surroundings. So when we got interested in these fibrous structures, we were looking again at natural principles, swarm behavior and plant movements, to try to understand how we could organize vertical linear elements to create synergetic wholes. And these tests we did also then informed the tower's geometry as well as its organization and structural behavior. So it's really, again, the way we start in the office, really sketching three-dimensionally and collecting these ideas that inform the design. And here you see the tower, the fibrous tower again. You see these bundles of tower that again then have sub-bundles, so to say. So it's all one profile of 35 centimeters of diameter that builds up the whole tower. So what you should see here is that it consists of 8 bundles which have different functions. The inner one have the circulation and the outer ones contain all programs, and then they are all intertwined into one whole. So we also worked with other amazing climate engineers we quite often invite to our project, Transolar from Stuttgart, and we were really interested in using renewable energy, but not in a way that you just apply it to architecture, but we really wanted to embed it. So we have architectural elements that could move and by movement create energy. And we also had low-tech measurements, especially in the park, how we would create microclimates with water and natural shading. Here you see, again, the generation of the tower structure done by Bollinger, Grohmann, Schneider. So again, the tower structure is emerging, so to say. So it's looking for the ideal position of these connections between the fibers. Yeah, and that's the tube. So this is really what you need to build it. And it's available everywhere, and also in Taiwan. So it was really a very clever idea by Klaus Bollinger to just use a standard profile. And then we were testing the structure and found out that it had many advantages. Not only that we could reduce the welding volume, since you only had to weld these small tubes, but also since the tower was open, it reduced the wind loads. And wind loads mean steel, and steel means cost. So it was really, in the end, we found out that we had a very efficient structure, and we were really able to build this tower with the real budget, although it looked very complex, and it had really very simple inherent rules. Yeah, so again, a view onto the tower and the museum, how it would have been built. For the observatories, we had the idea of increasing the area as plants would also do. So you would increase the views onto the surrounding. So here you see an inside view from the tower top. And then the city museum that creates an entrance to the park and the tower. And to the park side, there are these architectural elements that create these microclimates. So it becomes, they create comfortable zones in the hot summer. And the idea for the foyer areas was that the ceiling would be very articulated, and that the ceiling would be the element that would create the space and lead visitors through it. As well as in the tower lobby, where you would have these kind of intuitive geometry that would guide and create these spatial flows. Since the tower is embedded into these cycles of renewable energy, we wanted to display that. It would have been the world's largest vertical absorber covered with flexible PVA foil. And so it would gain a lot of energy during the day, but of course not every day would gain the same amount of energy. So we wanted the tower to show that to the city. So there would be days where it would be rather dark, and other days where it would be really bright. And also you see these moving pendulums that create directly light out of wind energy. So the tower would really become this living plant or organism that would also communicate this to the city. Yeah, unfortunately, it did not get built, but we're still looking for a client. So we have not given up hope yet that we will apply some of those principles in other projects. The next project is actually our most recent one. We just opened it a couple of months ago. On the other hand, it was also the project that took the longest. So we were starting this project already in 2007. It's an extension for a school, actually a very interesting school, a school for construction and building technologies. And this school wanted to rent out one of their halls and turn one of their fabrication halls into a concert hall. So they asked us to do a new foyer, an entrance landscape, and also do this new hall. So it was really interesting that you would have two completely different user groups. You would have the pupils that would go there to learn how to do brick walls and pour concrete, and then you would have people who would go to classical concerts at night. So again, we wanted to do something that would create a very distinct atmosphere and a very consistent geometry, but it will also do have many performances, so to say. So on one hand, it is structure, it creates a roof. It has to provide natural lighting as well as artificial one. Then we had this idea, again, of the ceiling as this guiding system that would lead you into the concert hall, but also into the school. And then we wanted to have something that would, in a way, correspond to the existing structure, but on the other hand, be very consistent in its own geometry. So we were looking at particle simulations. In this case, we got interested in viscosity because viscous liquids have this property of being very coherent and consistent, and on the other hand, they can create holes, and that was really what we needed. So we were, again, doing this three-dimensional diagrams and testing a lot. So this is the roof and the entrance landscape as well as the concert hall, and then we also did some office area on the other side. And in section, you see this idea of really creating this flow through the foyer. So we really wanted to open up the whole space, that you really get this transparency and this view throughout the whole space. And of course, also back out to the surrounding. So here you see how this roof performs a structure, but also generates light, and then inside it creates this continuity and also this guiding system into the concert hall. Many of our projects have a research part, and that also is due to the fact that they're experimental in a way, and sometimes to implement them, you really need much more effort, and you need to team up with engineers and experts. And in this case, the most important topic for the client was really to really be sure that there would be no cracks at all in the concrete. So we had to test the piece one-to-one. So you see here, this is our structural engineer. He really trusts his calculations. And we had to build this one-to-one and then put it under load and really prove that there would be no cracks at all. So here you see the reinforcement, the work of the structural engineer. And then what was really important was the testing of the foam work. Since the milling path really influences the surface articulation, so the play of light and shadow, and we tested really various patterns, and we also poured them in concrete. Actually, that's what the school itself did, so they were also involved in the project. And finally, we decided to go for the finely triangulated version, not only because it would reflect the precision of the digital design and process the most, and it would not look handcrafted, but also because the play of light and shadow was just intriguing for us. Yeah, there are these moments when you go to the construction site and everyone who's working there just sees a big mess, but you just see beauty. So we really like that, and but of course you can see what it means to have this formwork. You have to get rid of it again in the end. And there it was, and in the end, the final result, the finely triangulated mesh with a play of light and shadows. I think the client is really happy with it. They're really proud because they kind of have now these new piece of experimental architecture, and since they are really dealing with concrete technologies, they're really happy to have it. And we also got recognition from architects, since we got the recognition award for architecture this year from the country Salzburg, since it was highly experimental in terms of construction. Yeah, and then finally, I would like to talk about probably our most important project so far, because it kind of made SOMA going. We were really doing this competition, again, open international competition, on our couch in the living room without any office infrastructure at all. There were 1,000 registered architects for this competition. 140 submitted. Among them were invited ones like Saha and Shigeru Ban, Winnie Ma. So we really thought we do this for our portfolio, and we really liked the brief and the site. And then we won, and then we were in shock. And what followed then were 2 incredibly intense years where we learned a lot, and somehow it really was the beginning of SOMA. So there it is already, the finished pavilion at the day of the expo opening. The brief of the expo was actually very vague. It was just an amount of square meter, and the statement, we would like you to do a building that represents or symbolizes the theme of the expo, namely the living ocean and coast. And we really don't like architecture that symbolizes anything. So we were saying right from the beginning, we're going to do something that implements or incorporates the expo's agenda, namely the responsible use of renewable or of natural resources, but through a climate concept, and also in the end through the biomimetic approach of the kinetic facade I'm going to explain later. So here's the building site. This is Yosu in the south of South Korea. It has 300,000 inhabitants, and they have these former industrial harbor. The expo now revitalized. And this bank here is really where our pavilion is located. So as you can imagine, the relation to the expo site here alone designated as its main landmark. So it's visible from all sides. So we were aware that we would have to do a changing appearance with many faces to all sides. The other idea, or one of the main concepts from the beginning of the competition, was the idea of this coastline and to create a new meandering coastline through this aggregation of exhibition cones. So we aggregated these the exhibition spaces along this coastline, and then we transformed them to create the public spaces for the foyer. And in the end, you see, and this is the aggregation that came out of this. So this is how the building sits there now in the water, built into the open sea. Quite a challenge to build at that site, actually. And as you can see, it's very compact. It's made out of concrete, and the choice of this material is also due to the fact that we had to protect the building from the impact of large ocean waves, but also from the impact of salt water. While to the other side and to the expo, the building is very different. It's more like a walkable topography, and then it shows this kinetic facade that works with the architecture's own layers to create choreography and a moving pattern. And when you deal with these contrasting appearances, you also have to deal with the question how to merge or blend them. So here you see how these cones twist and then grow into this metal facade and then the kinetic facade. So this idea of continuity or twisting was the other main concept of the building. So again, this is this three-dimensional sketch we were doing and principle we were testing in our office. So the idea was to have these twisting surfaces that would rotate from the vertical to the horizontal orientation. And by doing that, they would generate all Mayer spaces. The vertical shows where you would immerse into and have these multimedia spaces, the best practice area on these horizontal platforms, and then the lobby that's connected to the promenade. So this one movement organizes, defines, but also divides these spaces through one gesture. So again, we test, we 3D printed it to understand it and to look at its effect. And here it is in the real building where people were streaming in and out of these curved walls and into the thematic shows. The lobby was a rather open space to contain huge crowds of people during the expo. You can see here the building creates this shaded area for the people, but you can never have enough shade. The queues were longer than that, of course. And then you have these open foyer and then the sequence of cones. So you enter here in the pre-show, you go into the main show, the post-show, and then you go up to the best practice area. So the cones also frame the view onto the ocean, and here you see the more flexible platform on the second level, where you would have institutions and NGOs presenting their work. In section, you see again this idea of this continuity. So the cones, the twist, and then grow into the kinetic facade and then back into the roof. And in the longitudinal section, again, the sequence of cones, the pre-show, main show, and post-show. And then, as you might have noticed, suddenly there are 5 cones. There were 6 at the beginning. So we had to implement this main cone very late during planning phase, which was anyway just 6 months. So the exhibition design changed, and then we had to react on that, and we had to implement the cone that was 20 meters high and 30 meters in diameter, which was quite a challenge, or not to say hassle, for the structural engineer. And as you can see here on the right-hand side, the construction side, very early construction, the concrete is not even poured yet, and steel work already begins. This was really very interesting time, as I mentioned before, but you tend to get nervous when you see that. So how can you do it? You need parametric models. You need to be able to quickly change also things if needed. And this is just to show how we, again, optimize, so to say, the triangular window. So we were looking for the different sizes we would need to get these gradients of windows to become as efficient as possible during construction. And here you see the windows then in reality. The windows were mainly there for after use, because as you see now, the building is a permanent one. Nobody hopefully built a expo pavilion out of concrete. The building will be sold and then have another use. So we really had to plan this possibility for natural lighting for the time after the expo. And here a view from the inside, from the cafeteria, and again the triangular windows. What we added to the brief was a third exhibition level. So, I mean, maybe some of you have been to expos and you know that expo is mainly about queuing. And actually that can become very frustrating when you just queue for hours and hours in front of these pavilions. So what we wanted to have is a freely accessible roof, a path you could walk up there and then enjoy the sight onto the expo and the really beautiful surrounding there. So here you see the path meandering between the cones, and then like an architectural promenade, you walk up along the cones and have the views onto the surrounding. And actually this became a very popular place, especially during late afternoon and evening hours, and then even more during nighttime when all these expo shows were going on. It was a perfect spot to look down at the whole area, and people were really doing their picnics there and enjoying themselves. And we never expected that this area would become so popular. As I mentioned before, it was really important for us that we would really embed the expo's agenda and not symbolize it, but really implement a climate concept where we would also make use of out of the geometry and create a synergy with our geometry. So we were working again with Transolar on this project, and there were many means, but one was natural ventilation, since we could use the geometry of the cones to create these airflows. The other idea was that we would use the height of the cone, so we would just condition the area where people would be walking around, while other areas where people would not access them, they could just be hot. So we used thermal stratification, and by that we could reduce the energy consumption. So the first step was reduction of energy consumption, and then using renewable energy to do the rest. The kinetic facade is an integral part of this climate concept. So you can see it in open and closed state, and below you see the simulation. So the whole building was tested and simulated in 3D by Transolar. And besides that, besides controlling the solar input, the facade was also the idea of having an analog media facade. So the idea that architecture itself is a medium already, and that we could use architectural layers to create movement and patterns and the choreography out of these layers. So when we won the competition, we had already proposed this kinetic facade, and we were in shock anyway that we have to build it, but we really had no clue how to build that facade, since we knew there was nothing out there like that. So we went to Stuttgart and met Knippes Hellwig, again amazing engineers, and they also do a lot of research at the University of Stuttgart into two things. One's into kinematics, but also into GFRP, and they were really amazed by the idea of having this seamlessly swaying facade that would have no hinges and would not be mechanical. And then we teamed up, and we were really proud that we could turn this project within this very short period of planning into a research project. So we also have the patent on this facade together with them now. So this is actually, again, a very simple principle, and it can be described with a simple paper model. You just have a strip of paper, hold it on 4 points, and then you move 2 points towards each other. And by these very tiny movements, the lamella bends and does this side rotation. So it's actually torsional buckling, something you want to prevent in architecture. You don't want architectural elements to bend. And we use this as a functional principle for the facade. So actually, it's not high-tech in that sense that the technology is high-tech. The material is known for years, but it's really the thinking, the different approach that makes it novel. So the lamella, all the lamellas follow the same radius. It's all 17 meters. It makes it really efficient in terms of construction. But of course, they all vary in length. So the whole facade is 140 meters. The longest lamella is 14 meters and the shortest 3 meters. So of course, they also all vary in the build-up. So actually, you will now shortly see how the lamellas were fabricated. And it's actually a very simple, hands-on process. As I said, the technology is not high-tech, it's actually low-tech, it's very known. You could have used one negative form, but since we had not a lot of time, we used 3. And here you see how these fiber mats are rolled out. So every lamella has a different build-up of these mats. They all differ in thickness. They're approximately 9 millimeters thick, so they're really very thin blades. And then they are L-shaped, as you can see. So they're stiffer on one side than at the other, and that's what results in this movement, in this opening up of one side. They're also elastically deformable. That's what GFRP can do. And yeah, so here you see how it's made. Actually, everything took place at the same time. While in the hall they were fabricating the louvers, outside they were testing them and they were programming them. So it was really, everything happened in very short time. So here you see already the mock-up outside of the fabrication hall. The longest and the shortest were tested, not only to see how precisely they would close and open, since that was also very important, since there's a lot of wind in Korea, and when the wind comes, the lamellas are kind of sucked back from the actuators, and they really have to close And so they were testing not only that mechanism, but only durability. Especially these points are really crucial. So they were testing this over months. The whole mock-up was running all the time to really see how these constantly opening and closing would influence these crucial points. So as I said, these motors, these spindle motors, these actuators move the lamellas just a tiny bit, and then the resulting movement is actually this big opening of the lamella to the side. So actually a very efficient way of movement. The principle of bending was deduced from plants' movements and came from the research that's done at the ITKE in Stuttgart. So if you're interested in that, we also have published a book recently where all this information is in there. I think it's also in the Bartlett library now. And here you see how it's opening and closing. So it's really, there's nothing behind. It just opens seamlessly. And I think that was also why people were so astonished, because the movement where you don't see the cause is still one of the strongest sensations you can have. So these up to 50-meter long blades were just opening without any construction behind. So you could actually move all the lamellas individually and create all possible patterns. At the expo, they now just did this opening and closing pattern. But since the building will get a new owner soon, and hopefully a cultural use, we really hope that the new user and owner will really like to play with it and probably invite artists to play with this analog media facade. So in principle, you can use it during the day, but also during night. The client wanted to have LEDs, so it also works as a conventional media facade, something we were not really longing for, but well, we had to implement it, of course. It's the client's wish. So yeah, it worked both ways. During day, had this analog choreography, and during night, it was playing whatever the client wanted to play. So here you see the LEDs on the outside of the lamellas, and again, yeah, in the opened and bended state. Yeah, so the lamellas are really a combination out of geometry and material performance, and although they're really simple, they create a very complex and astonishing appearance when they are moved. Yeah, and here it is, the building with its eyes closed. The expo is over, so it's waiting for a new owner and a new use. And as I mentioned before, the book is in the library. Yeah, and if you have questions, well, we are here and happy to answer them. Thank you for your attention.
Unit 15 has to answer the questions. They have to prepare some, right?
I want to. Yes.
I come from an interaction design background, and I'm always really interested in how people move through buildings and how they perceive a building. And when you were talking about the Taiwan Tower, you said you were talking about intuitive geometry. So I was wondering how you decided which kind of geometry is intuitive.
Yeah, that's a very speculative thing. I think one thing about intuition is that you can't prove it, right? And you can't measure it. That makes it so tricky. I think, on the other hand, really lots of decisions you do as an architect are intuitive. Because, I mean, that's our tool to deal with complex questions like this. something's going on, so many input, we just run intuitively, or we just do something. And I think that's how you can, or I think the only way to do that is experience. I think it's really just like a musician trains and plays and plays and plays a piece and learns it by heart. That's what you do when you do architecture. You do again and again and again and again. And in the end, you kind of develop something like intuition, or it's also something which is when you go and visit your own building, and you go there for the first time on construction site, and then you go there and it's finished, and you stand in front of there and you know what it is. You know it so well. And you've just been sitting in front of a screen all the time. So that's something I think you can't really explain, and it's a tricky thing, I agree, but I think it's really experience in a way. You need to test. Yeah.
So did you learn from seeing how people move through your building?
I think it's from observing people, but also from how you yourself do it, because I think we're all different, of course, but on the other hand, not so much. And I think, yeah, observing and experiencing, we just like to visit other architects' projects. We just really go, and everywhere where we are, we try to visit famous or interesting buildings. Just because you need to experience it. Yeah.
For the building, I'm not clear is steel structure one or concrete one. I saw both structure appear and several pieces of concrete one. Can you explain more?
Yeah, the building is really twofold, so to say. There's a concrete part, so the cones are all made out of concrete. And then to the other side we have steel. I mean, Stefan, maybe you want to answer that, but it comes also. I mean, we were asked also by other people, why don't you want to have continuity and everything needs to be concrete or everything needs to be steel? And well, also to do everything under steel was tested actually, because it would just have been much quicker to produce, and concrete is. I mean, you do the building twice. You do first the formwork and out of steel, and then you pour the concrete. So I mean, it's cost intensive and everything, but in the end, it just proved to be the right technology for that place and that time. And so it was and in the end, we do not believe in this all-in-one material, because in the end, a facade is different than a roof, than underside. The building has different phases and different functionings, and I think it's for us it's really okay to have different materials. The question is, how do you bring it together? But I'm fine, because the facade is not. I mean, this all-in-one is it's also interesting, but maybe we also do that fine. But in this case it just turned out the other way.
The main supporting structure is steel.
The concrete, the cones are concrete, there's the structural elements, and then the other part of the facade and the roof is steel. Yeah.
You seem to have a very close relationship with different consultants. And I would call them modern consultants in your case. They're not just giving you some advice. There seems to be a very intense working relationship, in particular for you as a young and relatively small team to build such a large building. And when I think about the Taiwan Tower, would you have won it? It would have been a massive sort of enterprise for such a young small team. And my question is to do with at what stage is the engineering kicking in? Because you mentioned a lot of that, and a lot of the projects are very dependent on extremely good engineering, on people who understand what you want to do, who in fact, more than understand, contribute to the project. It's sort of the Taiwan Tower would be unthinkable without the tube idea. Anyway, it would become much more clunky and aesthetically sort of rather, it would lose actually all the beauty. And I think, again, in this one here, to build these columns, I guess to convince even the Korean client and the contractor there to build that complexity without the right engineers is probably unthinkable. How early on do you get them involved?
As early as possible. I would say as soon as we have the first concept and we know the direction, we really try to get them into the office and discuss, and because I think it's really, architecture is this interdisciplinary.
But then how much do they change your scheme?
Well, not a lot. Sometimes it helps. I know, I honestly agree.
With the Taiwan Tower, for example, we had the idea that we would like to have a fibrous tower from the beginning on.
Yeah.
And Oliver Grohmann at the beginning said that this is unusual and you would rather go for big cross sections because this they know from bridges in horizontal position, but this is usually very hard to construct. It's interesting. Probably we should discuss it more in detail. Can you imagine having, let's say, this kind of hollow cross section with a lot of tubes and not big, because we also have this bundle of tubes and they are all tubes inside as well, yeah. But that they optimize the.
But you need to have design-sensitive engineers that also like to think in concepts. I mean, you need to have an idea, an aspiration you share. I think that's the most important thing. And if you have consultants who are not used to this, I mean, we have Francis Archer from Arup, and we're so happy that we have him in Unit 50 now. I think it's so great also for the students that they now also have this kind of process, that they're sitting together with him on the table and discussing, and also find out that certain things or certain decisions you have to do can improve the project. And of course, as the architect, you have to develop your feeling when it's not going in the right direction, and you.
No, in a way, I'm asking something a sort of an obvious question. You know, obviously the engineering kicks in very early on, but I think what is not obvious is that you get the right engineers and the right sort of people to help realize these projects.
Yeah.
And for instance, during the Taiwan Tower, some of the other competitors made a comment that they lost the scheme because they had the wrong engineers involved. Yeah. And it happened to, I think, 2 or 3 teams actually. They were part of the last 5 or 6, and they lost the scheme because the engineering was not right. It just didn't match. And in fact, you might remember there was a scheme by a Romanian team, which was seen as potentially the scheme that was going to win. And they lost it because the engineering couldn't crack their building. And so I think, I mean, having been a bit through this sort of same problem as well, if you don't get the right people involved, it simply won't work. Which in a way makes me think that in the environment of a studio, if you don't have the right input at the right time, the whole thing doesn't make sense. Yeah. And I think your work just was a clear explanation of that. You sort of couldn't do it alone with the wrong people. It just simply would not going to happen. It was not going to happen. And surely, for instance, the whole membrane that you got the patent from.
Yeah, absolutely.
Phenomenal, this sort of relationship, which sounds so easy. It's sort of, they just did it, easy stuff, but incredibly difficult to get the right people.
Yeah, but if you have the interesting projects, you get them on board, right? And that's crucial to get the team together, right?
I think with the Taiwan Tower, the Romanian team they never worked before with these engineers, and I think it's also very important that you continuously work together with the same or the kind of family of the same engineers and specialists, because then there is also this kind of trusting each other, you know each other, and I think that's what was the problem for them. They never worked with them before. I think probably because I had a chat last year with them as well. They said it was horrible.
As an engineer, I mean, Stefan's completely right. It's to get full engagement of a team. capable of delivering what ultimately is a multidisciplinary piece of design, you have to know each other and understand each other and fully engage. You have to understand what you mean by what as an engineer, to understand what architects really after. What does he really mean when he says he likes that or something like that? And then make suggestions. So you have to understand each other. And that takes time. So you can't forced marriage generally doesn't work. But it does vary. Some architects are okay with forced marriages with engineers. It depends. It depends whether you treat it as an integrated, fully integrated design or as a layered design. And if it's fundamentally layered, maybe it matters less.
Yeah, I would absolutely agree with that.
How much, another question is, how much do you test these projects in models or through models?
Actually, quite a lot of the Expo pavilion we built in the end. I think only like 3 huge models like that, and we also then smaller ones, and then we took them to Korea a lot in airplanes. Can't recommend that. But we really also like to build them in our office. We don't often have model builders, but it's such a great tool of communication also with the client. It's interesting, but if a model's there, it gets a different energy for them. And it's different than just a rendering. I think they're so used to images that if you really have a good model,
But it's also a problem because the model building is very expensive and we would love to do more, but it's just not within the budget in most projects. Especially with competitions, it's very difficult to do huge models and to test your ideas on models. And I really would love to do more, but it's hard to find the time and budget and people to do so.
Yeah. We're just waiting for 3D printers to get cheaper.
It's better with real projects, with building projects, because then you can reserve a small budget and then you can test and do the model building which you would like to do.
So just wondering on the topic of collaborations, it also seems that you have a relatively strong research aspect to your projects. How do you manage to get, because the academic world to me seems to move a little bit at a slower pace than the real world. So how do you manage to get that collaboration working at a very quick, real project pace?
I think we really try to bring in our interest into the project. So we're always happy if it happens that we can then learn by doing a real project. I think it's research in a very applied sense, though. So I would not really call it like academic research where you then have your thesis and you test it and you make really scientific tests. And I think it's I mean, we also do these things, but it's tricky. It's not always easy, and not every project allows you to do that. But I don't really have an answer for that question. I would like to have one.
How does your work at universities, working with students, and everything else that you're doing here, how do you feel that fits in or helps, or how does that fit into your practice of real competition?
I think it helps a lot. It keeps your brain active somehow. It's like I mean it's probably when I was a student myself, and I was constantly looking at other people's work and reading and doing it, and now it's a bit that also the students do that, and then they come and show, oh, I found this project, I found that article, and it's a bit also, of course, they do also part of your research, so it's also this that they feed, of course, your ideas, and I think that what we really like is we really think that architecture is a discourse, and that you really have to be able to have a standpoint there and also make a statement and find arguments and be articulate and talk about architecture. And I think that's what you, when you're just sitting in the office, you kind of get into these working modes where you're just doing things and you tend to become pragmatic and a bit, you know, also at some point you kind of lose these aspirations. And I think when you're working with students, it opens up again a bit your horizon. I think, at least for us, it's very refreshing. I think this exchange of ideas is, I mean, it's also that somebody says something and you have suddenly you have an idea about something. It's really, yeah, it's just really an exchange.
So architectural theory, really, is architectural theory and reading, intellectualization, if you like, or how does that fit into you?
I mean, for me a lot, because that's my second job in Vienna. I'm at the theory department there. So actually, yeah. So I think that's, but it also it feeds in there because in Vienna I have to force my students to write and really have precise arguments, and then on the other hand, doing design, I would also like to free them, of course, from that, because I still think you need to be expressive and free to design. You can't just argument everything, but on the other hand, you also need to be very precise and clear. And I think that's somehow for me very important. How to make. I mean, I would really like the students to really know what they're aiming for and really be trying to be as precise as possible in their results. I mean, yeah, and theories anyway is so important. I mean, I couldn't do without.
Sorry, probably it's the right time to ask this question because as you mentioned about your study time at the university, and who would you say the most influential architects or the architects who influenced you most while you were studying?
Well, of course. That's a
difficult
question because there are many architects that influence you in many different ways, right? But I mean, it's funny because I was educated for 8 years. I studied for a long time. Stefan is by Wolfgang Pritz, which if you would know him, he's, I mean, he just has to influence you because he would throw your model onto the floor and step onto it, and he would really appear in your dreams, right? So he's a very strong father figure and a very impressive architect. So we learned so much from him. It's really incredible. But on the other hand, I would say that then just spending this year at the Bartlett probably influenced me much more because it was just different. Right? It just turned my head around a bit. And so it's not only, you know, it's so many things. And it's also what Marcus said, some things have to happen at the right time. And then also people you would never think that they influence you suddenly have an influence.
Yeah, sure.
Yeah.